Hello, this is Dr. Viv. In this video, I would like to focus on an important property of hyperbolic functions. Let's first recall what these functions are. So the sine hyperbolic, also sometimes called sinh, of chi is e to the chi minus e to the minus chi divided by 2. Cosh hyperbolic chi is e to the chi plus e to the minus chi divided by 2. The other functions are defined using sinh and cosh. For example, tan hyperbolic is sinh over cosh. Very similar to trigonometric functions, so I won't write the rest. I would refer you to any book on calculus for a review. My main concern here is the connection between hyperbolic functions and trigonometric functions. There actually exists a connection thanks to the great formula by Euler. Euler's formula, recall, is e to the I theta is equal to cosine theta plus I sine theta. Theta here is measured in radians. Similarly, e to the minus I theta is cosine theta. If I change theta to minus theta, the cosine term will be unaffected because cosine is an even function, but the sine will become minus sine. So what I can do is I can set chi equals I theta in my trigonometric formulas, in these hyperbolic formulas, and see what happens. So I'm going to put theta equals I times chi. Let's see what happens. In other words, I'll put chi equals minus I times theta. Okay, so then I'll get from the first formula, I'm going to get e to the chi is equal to cosine I chi plus I times sine I chi. In the second formula, I'll end up getting e to the minus chi is equal to cosine I chi, because theta is equal to I chi, recall, minus I times sine I chi. I can add these two and subtract them to get those. So if I add them, I'm going to get cosh e to the chi plus e to the minus chi divided by 2. I'm going to get 2 times cos, and if I divide by 2, I'll get cos I chi. But cos I chi is the same as cosh chi. So that's the big result I have, connecting the trigonometric functions and the hyperbolic functions. In exactly the same fashion, instead of adding these, if I subtract them, these two terms will cancel out and these two terms will add, and there'll also be an I left over. So the corresponding result for sine is sine I chi is going to be I times the hyperbolic sine. What these results do is that they show that in some fashion the trigonometric functions and the hyperbolic functions are actually connected if you are willing to expand your range to the imaginary axis. This also leads to something called Osborne's rule. If you'll notice, the cosine and the cosh are somehow directly related, but the sine and the sinh are off by this factor of I. So in any trigonometric formula with a sine squared, if you try to get the corresponding hyperbolic formula, you will have to multiply it by I squared. I squared is -1. So Osborne's rule summarizes these results. Osborne rule says in any trig identity, you replace cosine squared by cos squared, and you replace sine squared with negative sinh squared because of the I squared. So let's take a simple example of this to figure out how you can cut short your work. So suppose the famous identity in trigonometry is sine squared theta plus cosine squared theta is equal to 1. The hyperbolic equivalent of this is going to be negative sinh squared chi plus cos squared chi equal to 1 by Osborne's rule. Okay. The other interesting connection between the trigonometric and the hyperbolic functions occurs when you look at alternate ways of doing the same problem. So let's consider a basic example of integration. I want to integrate the following function. I equals integral of dx over the square root of x squared minus 1. There are actually two ways to do this. The first way is using what you would normally do in the first course of calculus, which is a trig substitution. The trig substitution you would use in this case would be x equals secant theta. Then you'll notice that x squared minus 1 is the same as secant squared theta minus 1, also known as tan squared theta. Dx would be secant theta d tan theta d theta. So if you substitute this, your integral would simply become secant theta tan theta d theta in the numerator, and in the denominator, because it's a square root of x squared minus 1, you'll just get tan theta. The tan thetas cancel out, and the integral of secant theta is just natural log of secant theta plus tan theta. And the last step is to reinstate the variable x. So that gives me natural log of x because secant theta is x. And tan theta is just the square root of x squared minus 1. Plus c, of course. That is one way to do this integral. The second way to do this integral is using, and this hardly gets done in a calculus course because nobody ever seems to like the hyperbolic functions, but they are just as valid as trigonometric functions because of the connection between them in the complex plane. In fact, you can see this integral is much easier to do using hyperbolic substitution. So let's start with the same integral, but this time we'll use hyperbolic geometry. The substitution I want to do is set x equals cos chi. The reason for that is I noticed that if negative sinh squared plus cos squared equals 1, then I can write cos squared minus 1 as sinh squared. Okay, so let me rewrite that. Cos squared chi minus sinh squared chi equals 1 is the same as saying cos squared chi minus 1 is equal to sinh squared chi. Now if x is equal to cos chi and cos chi is that, when I differentiate cosh, e to the x becomes e to the x again. But when I differentiate e to the minus x, I'm going to pull a negative sign in front. In other words, when I differentiate cosh, I'm going to get sinh. So when I find what dx is, that is just going to be sinh chi d chi. What does this integral give us under these conditions? I is equal to, the numerator is just sinh chi d chi, and the denominator, if x is cosh chi, the square root of cosh squared chi minus 1 is just sinh chi again. The sinh cancels out and I simply get chi. Well, chi is the cosh inverse of x plus c. So we have two very different looking results. On the one hand, this integral is the natural log of the absolute value sign is not really necessary if we restrict the range of x. If you notice, this integral does not make sense unless x is bigger than 1. So if x is bigger than 1, then this will never be, the absolute value sign will never be necessary. So I can leave that out, but I'll put it anyway. And this is the other result. If you look at this, it's like night and day. There seems to be no relationship between these two, except that trigonometric substitution gave you this, hyperbolic substitution gave you that. But a single integral cannot have two different answers. So what we have indirectly done is given an alternative proof for the following result. The arc cosh of x is the same as the natural log of x plus the square root of x squared minus 1 for x bigger than or equal to 1. In this manner, you can actually choose suitable integrals and get the value of arc cosh, arc sinh, arc tan hyperbolic, and all the other inverse hyperbolic functions can be written in terms of something else which is not hyperbolic, such as ordinary functions like logarithms or ratios of logarithms. So this is a very interesting subject because it all stems from Euler's formula tying up two different ways of looking at trigonometric and hyperbolic functions and then using it to advantage by using some integral and doing it using trig sub and getting one result, and doing the same integral with hyperbolic sub and getting another result, and setting those two results equal.